in this module we will discuss displacement current. This is a very important part of Maxwell's equations, and this completes our discussion of the laws that govern classical electromagnetic theory. If you have viewed the previous modules, you might have observed that in the beginning we did not let the charge distribution vary with time, we did not let the current vary with time, and the fields that were generated because the charge distribution was static with respect to time and current distribution was static with respect to time, we got the fields which were also static with respect to time. The electrostatic field was because of the static charge configuration, and when we allowed the charges to move in time, creating a current, right, that current was steady current or sometimes called as DC, and the corresponding magnetic field that was produced was also static with respect to time. There was no time variation to the fields, and we obtained certain laws which were expressed both in the integral form as well as in the differential form. But when you look at module about Faraday's law, then you will see that we relax this assumption that the fields are time invariant. We let the fields vary with time. The magnetic field, if you allow it to vary with time, it would create a time varying magnetic flux, and if there was a complete circuit, a closed circuit, it would induce the changing magnetic flux that is linking to the circuit would induce an EMF, right? And this EMF is a quantity that is related to the line integral of the electric field. So clearly, if the magnetic field were to be changing with time, it would create a time varying EMF, which would imply that the electric field now has to be time varying, right? And we expressed this Faraday's law in a compact form by writing this as curl of electric field would be equal to minus del B by del T. This was the point form for Faraday's law. What is the physical meaning of this one? Physically, it means that you can consider a loop, okay, almost a closed loop is what we are considering, and when you let the magnetic field passing through this loop change with time, right? So if this B field were to change with time, then there would be an EMF induced, a current would flow in this circuit and an EMF would be induced, and EMF is something that depends on the electric field. So what we have, and you can do this one at different points in space, right? So with curl operation, what we mean is that this radius of the loop keeps on shrinking, so that you are actually evaluating this at a particular point in space, and at any point in space you can actually keep doing this. You know, you can imagine loops around those points of vanishing radius, and if you look at the EMF induced will actually depend upon the amount of magnetic flux linking that is changing with respect to time. So if the flux that was changing with respect to time all over this place, then there will be an electric field that was induced that would also be changing with space, right? So the electric field induced here would be probably different from the electric field that would exist here, and that field would be different here depending on the strength of the magnetic field variation. So if the magnetic field variation were to be uniform in the entire region, the electric field would be same, but it would also be varying with time, right? So you look at this equation of curl expressed in the point form for electric field or for Faraday's law, you would see that if B field is varying with space and it is changing with respect to time, and at any point around space, if the B field is changing with respect to time, it would create a changing magnetic field which would create a space varying electric field, correct? So the field around this would actually be varying with respect to this, varying depending on how much the magnetic field is changing, right? So here you have a space variation of the electric field related to the time variation of the magnetic field. Of course, if you evaluate this curl operation at different points, you will actually see that electric field itself would be varying in space, because the time variation of the magnetic field would be different at different points, okay? So you have all these combinations, you have inhomogeneous magnetic field varying with time, you have inhomogeneous magnetic field not varying with time, homogeneous field varying with time, and homogeneous field not varying with time. In only the cases where there is time variation will there be an EMF that would be induced, and this EMF induced will change the electric field itself. So the electric field is no longer actually a static field, it is actually changing, And more importantly, if you take a hypothetical point charge around a region where the magnetic field is changing and you just go around the magnetic field in whatever direction that you want, there will be so in the earlier case for the static one, you could go around a loop, but the potential difference would actually have been 0. The EMF around a closed loop was equal to 0, but clearly that would not hold in this case, because as you move around, by the time you have moved the charge around one revolution, in that time the magnetic field would have changed and it would have resulted in a different EMF value. So when the hypothetical charge comes back to the same point, it would no longer be at the same potential. The immediate effect of this rule is that, or this law is that, previously what was considered as an equipotential surface, such as the conductor, is no longer an equipotential surface, correct? You can imagine a conducting surface, and then you see that by the time you have taken the loop around the conductor, right, or inside the conductor, if the magnetic field were to be changing in that time, then there will be an electric field induced, right. So if you do this from point to point on a conductor, you will see that the electric field will not have will not have the same potential at different points. It actually will, the potential of the conductor at different points will actually change, okay. And you can show later that this change has to happen. You have to have the potential difference to be changing from point to point if you have to convey a time varying energy or time varying signal from one point to another point. And it is precisely this rule that conductors are not equipotential when time varying fields are present is used to construct transmission lines, waveguides, antennas, so on and so forth, okay. So the causality for Faraday's law seems to be that we have lost the curl of electric field equal to 0 relation. Now the curl of electric field is no longer 0. In fact, it depends on how much the magnetic field is changing there, right. So if the magnetic field is changing, electric field will have to change, at least with respect to space. This is what Faraday's law was about. So if you want to kind of summarize what Faraday's law is, it simply says that if there is a changing magnetic field in a point of space, there will be a space variation in electric field. Now from symmetry, you might question that is there a way in which changing electric field or changing electric flux density, to be more precisely, the changing electric flux density or flux does not matter, if the electric flux is changing with respect to time, will there be magnetic fields induced, right. Am I looking at some sort of a relation which would tell me that there is a quantity which we can call as magnetomotive force, just as you had a quantity called electromotive force, which was the line integral of EMF was the line integral of electric field, right, between any 2 points. You can similarly talk about H dot dl and call this as magnetomotive force, okay, in analogy with the electromotive force. So the question that we are asking is, will there be any EMF induced, will there be any MMF induced if there is change in electric flux density, right. Will this happen? Will there be a situation where the electric flux density associated with a conductor or a circuit would change and it would introduce magnetomotive force, which would mean there will be a changing magnetic field, correct. Now in point form, you might be expecting for us to write curl H is equal to minus del D by del T. Why have I written del D and not del E? The reason is clear. In this Faraday's law experiment, or in the Faraday's law expression, the quantity that we were interested was the magnetic flux, and magnetic flux is dependent on B. So by the analogy here, we have used electric flux, and we have also kept a minus sign, but as you see, sign is just a convention to determine whether EMF is positive in a given sense or not. So the sign is not very important for us, but the important point is that if there is time variation of the electric flux density, will it induce space variation of the magnetic field? Would it be possible? We will explore whether such a situation is possible by considering one of the classic examples of displacement current density, okay. So we will see how this classic example tells us that this relation which we have written, this is our relation which we can say hopeful relation, that is we hope that this relation would exist, and this relation we will show that it actually exists, not in the form that we have written but in a slightly different form, but nevertheless this expression is true. We do have changing electric flux changing the magnetomotive force, inducing a magnetomotive force and hence inducing a magnetic field. Okay. To show that this is what would happen, consider the classic case of a parallel plate capacitor, okay, connected to, this picture may not be very nicely written, but I have a parallel plate capacitor. Inside the parallel plate capacitor I can put a perfect dielectric. I will also assume that the plates are quite large compared to their separation, right. So the plate cross section is quite large compared to their separation, so I can actually don't have to worry about the fringing fields, right. Fringing fields would exist wherever there is cross section which is actually similar to that of separation and is equal to the cross section. So this is my ideal capacitor, okay. So the capacitor is producing a voltage, let us say V0 sin omega t, some frequency omega, not really important what frequency that is, and then we ask several questions. One of the first question that we would ask is whether there will be a current through this loop, right. This is forming a closed loop except for this capacitor gap, okay, except where the capacitor is located. So will there be a current in the loop? What would circuit theory tell us? Answer is yes, there will be a current, and let us call that current as some IC, okay. Let us call this current as IC, which is the charging current for the capacitor. If the capacitor has a value of C capacitance, then the charging current would be C dV by dt, which would be C or omega C V0 cos omega t. If you differentiate V0 sin omega t, you will get omega V0 cos omega t, and then you can use the classic expression that we developed for the capacitor, right. For a parallel plate capacitor which is filled with some perfect dielectric of dielectric permittivity epsilon, this becomes epsilon A by D, where A is the area of the capacitor, the cross section area of the capacitor, and D is the separation between the two, and there is cos omega t. This is the charging current that we would expect. Now if there is a current inside here, right, will there be a magnetic field associated, and will that magnetic field be changing with respect to time? To answer that, we need to see what happens when there is a current carrying conductor. What does Ampere's law tell us? Ampere's law tells us that whenever there is a current carrying filament, for example if this is my filament and this current is passing through this filament, right, there will be a magnetic field surrounding it, right. This is the magnetic field that would surround, the magnetic field lines would be surrounding it like this, correct. We have calculated what is the magnetic field around this current carrying wire, and if there is a current I, the magnetic field will be obtained if you look at a closed loop integral of H, right. This is what Ampere's law tells us. Whatever the current that is enclosed by that closed contour, so let us call this contour as some L, okay, to indicate that this is actually a loop. I could have used C, but I have already used C for capacitor, so I do not want to confuse two C's. So I am using this L to stand for loop, okay. So to this circuit I will consider a loop, okay, call this as some A, B, C and D, and let us say the direction is chosen in such a way that you go from A, B, C, D to A, okay. So this is the loop that I am considering, and then to this loop I will say whether there will be a magnetic field, and the answer would definitely be yes, because this current enclosed can actually be written as integral of J dot ds, where S would be the surface that is encapsulated by the or enclosed by the loop, correct. Surface is enclosed by the loop. So let me consider a surface, okay. Let me consider a surface over here that looks like this. Remember, there is no specific way in which I have to consider the surface. This is what this law tells me. It does not matter what surface that is, as long as this surface is completely enclosed or some surface is actually bounded by this loop L, then the current enclosed must be given by the current density times or the surface integral of the current density through that particular surface. So let us call this surface as S1. I understand that there are things which are getting very crowded over here, so let me rewrite by expanding that region around where we are interested. So there is a charging current here, this is the current carrying filament, this is where the capacitor is sitting, okay. I mean just exaggerating the figure so that you can keep track of loops and surfaces. So this is the loop A, B, C, D, A. So this is the loop, and the surface that we considered S1 was the one that was in this fashion, right. So this surface S1 actually meets the filament at one point, and the current density here would be, current is actually coming out in this fashion. So the sense of rotation I have taken is such a way that current and this loop would form the right hand rule, okay. The fingers would curl around the loop direction. What is the current density here? Well, technically the current density here goes to infinity, but when you are multiplying that with a vanishing surface area, the result will be a finite value, okay. If you are not very happy with this infinite current density, you can actually assume that the filament is having a short radius of say r, and in the limit of r going to 0. So the current density can be assumed to be uniform out, okay. And if you look at this surface, the current density vectors are all uniform and coming out. And if you integrate the current density over the surface area, which is this surface area over which the current density is non-zero, then you will see that this current should exactly be equal to IC, correct. So this current enclosed must exactly be equal to IC, and everything seems to be fine. So the point form of Ampere's law seems to be fine even when there is time variation of the current. What happens if the current is not varying with time, or more precisely what happens if this EMF source that I have connected is DC voltage? Then the capacitor would actually act as a open circuit, right. It would charge to whatever the voltage that you have connected, and once that charging process is over, and in this case where there are no resistances in the conductor, the charging process is infinitely fast. The moment you turn on the DC voltage, the capacitor charges, then it becomes open circuit, then the current through any element will be equal to 0 because the potential is exactly equal, so there is no possibility of a current. So for the DC case, we anyway get 0 current, and that 0 current is what is predicted by this Ampere's law as well. Now it also seems to have predicted the correct value of the charging current even when the charging current is actually varying with respect to time, correct. I enclosed is actually turning out to be the charging current even when the charging current is varying with time. Why is the charging current varying with time? Because I have created a time varying voltage, right. So I have applied a time varying voltage resulting in time varying current, which is correctly seen to be predicted by Ampere's law. So where is the question of electric flux here? What is wrong with this result that we have obtained, or are we wrong? To answer this question, let us imagine going to a different surface. Remember, there is no restriction on the surface that I am going to consider to apply the right hand side for Ampere's law. All that I am required to do is that surface also is bounded by the same loop A, B, C, D, A. So let me now consider a surface which would go in this way, okay. This surface let us call as S2, and now I want to find out what is the current density vector here, right. Assume that this current density vector is uniform and it has to be very concentrated out there, just on a point that is coming out where the surface is cutting through the current density vector J, right. So this is my current density J. Now what is your prediction? What is the current density here? Well, this is a capacitor, there is a gap inside. You can actually, instead of putting it with a dielectric, you can replace the dielectric by air and there won't be any charges inside. So there is no possibility for me to actually have any current through this gap. Even with a perfect dielectric, there will not be any current through this because there are no free charges. As long as there are no free charges, there is no charge motion, there is no current. So if I apply the right hand side of Ampere's law to this, I will actually see that this should be equal to 0, right. The I enclosed would be equal to 0 on surface S2 if I consider surface S2, and it would be equal to the charging current if I consider surface S1. Now for the same left hand side I am getting two different values of right hand side, and I can pick and choose whatever value I want. If I pick surface S1, then no change in Ampere's law is needed, okay. But if I pick surface S2, then I am actually predicting completely different. Moreover, if the charging current is here IC until the point it reaches the gap, and in the gap the current is 0, one of the other laws is also breaking down. KCL is actually breaking down, right. KCL is not working here because current incoming at a node is not equal to the current that is outgoing. So what is really happening on? What is really happening here? What is going on that is wrong? First of all, we agree that this is wrong because the left hand side hasn't changed. It is still the integral of h over the loop L, right. The right hand side seemed to give me two different values depending on which surface I have used, and I cannot have two different values for just because I decided to choose two different surfaces. So today I might choose surface S1, tomorrow I might choose surface S2, and that cannot be determined. The answer should not be determined by our arbitrary way of choosing the surface. There has to be some consistency, and this is precisely what Ampere's law does not have, okay. Ampere's law is said to be inconsistent when there are time varying fields involved, okay. The textbook way of showing you that there is inconsistency is very interesting. So you start with Ampere's law, okay. So this is what Ampere's law would tell you in the point form, of course. Then you apply a vector operation called divergence on both sides, right. So you apply the divergence operation on both sides. I immediately recognize that del dot j must be equal to minus del rho v by del t in general, correct. Of course, if you are going to apply this one in a case where there are no charge variations, then del dot j will be equal to 0 and everything seems to be fine. Why? Because this expression divergence of curl will always be equal to 0, always. It will be equal to 0 today, it will be equal to 0 tomorrow, and it will be equal to 0 as long as you are alive and we are alive. So because this is 0, clearly that would force del rho v by del t equal to 0 everywhere. Now if I have some charges, and if there are actually charges which are vanishing in a given region of space, I cannot always say that rho v is 0 there. There is some charge, and this charge configuration is changing with time. So because of that, I cannot all the time say that del dot j is equal to 0. So clearly something is wrong. So this would not be equal to del dot j for all the time. What should we do? Well, this is point where Maxwell recognized that Ampere's law was initially stated only for static currents, or the currents which was steady currents, sorry, not static, steady currents, and when there are time varying currents involved, the Ampere's law would not really work there, okay, because we have forgotten that electric flux which would be changing would also start to impact on the magnetic field. Of course, there is Maxwell arrived at this very profound way of observing this after a lot of thinking, and one of the things that I have to mention here is that Maxwell did not have the advantage of using vector analysis. I mean, true, the way I have shown you that there is inconsistencies mathematically is that I have shown you that there is mathematical inconsistency because divergence of curl of h is equal to 0, right. However, when Maxwell formulated electromagnetic theory, vector analysis was not yet invented. So he did not certainly arrive at inconsistency in this fashion. He arrived at inconsistency in various other fashions in this particular way with a capacitor kind of a situation, and then recognized that he has to modify Ampere's law, and he modified it. This modification he did by a very clever idea, okay. We have del dot j is equal to minus del rho v by del t. Of course, again I have to emphasize that I am working everything in vector domain, but Maxwell had not seen vector analysis, so he used a different approach, but the results are essentially same, okay. So in our mind, so if Maxwell knew vector analysis, this is how he probably would have proceeded. So he would have started by del dot j equals minus del rho v by del t, and he would have recognized that rho v can be written in terms of d field, right. Divergence of the electric flux density gives me the charge distribution at that particular point, correct. This is coming from Gauss's law, which states that if you integrate the electric flux density over the closed surface, this would give you the total charge enclosed, right. The point form of this is this expression. So, he simply replaced, or he would have replaced rho v by del dot d, giving you minus del by del t del dot d, and he would have also interchanged the divergence and time operations. So, that you would have obtained minus del dot, or you could say minus del dot gradient, sorry, del d by del t, right. Now, I have two divergence operations on left and right. So, I can actually pull them together and write del dot j plus del d by del t must be equal to 0, right. Now, this is looking exactly like some del dot del cross h equal to 0. In fact, this is one of the two laws of vector analysis. Given any field which has 0 divergence, then that field can be expressed as curl of some other vector field. If any vector has 0 curl, then that vector can be expressed, or that vector field can be expressed as gradient of some other scalar field. Okay. So, invoking these ideas from vector analysis, we can proceed by saying that j plus del d by del t must be equal to curl of h. Okay. Or the traditional way of writing this one is to say that curl of h is equal to j plus del d by del t, and this is what is called as modified Ampere's law. What has been modified here? What has been modified is this addition of a term called del d by del t, and this is called as displacement current. The reason why this is called as displacement is because d is called displacement vector. In earlier Maxwell's time, d was called as displacement vector, and this del d by del t performs exactly the same function as the regular current density function would do, right. J, in order to distinguish between this displacement current, we sometimes call J as conduction current, okay, or it could also sometimes be equal to convection current, although we are not really going to consider convection currents in our course. Okay. So, we have two currents now. One current is because physically charges are moving, okay, and this movement of the charges inside a conductor constitutes a conduction current. Now, there is another term which is actually the variation of the flux density, electric flux density, and that also performs the same role as that of the conduction current, and therefore, this is called as displacement current. Well, this is density again, because to actually get the displacement current you need to integrate over a closed line and an over closed surface, right. So, this is the point form of modified Ampere's law, or sometimes called as Ampere-Maxwell law. When there is a possibility of no conduction current, as it would happen inside that of a capacitor, there is no conduction current, there are no free charges for us to carry the current. So, in this case J will be equal to 0, but what will be non-zero is del d by del t. So, del d by del t will pick up whatever the charging current IC is, and in that process give you the continuity of current, okay. Otherwise charges would have piled up, right, but this is a situation where you cannot really have that one. So, the role of the conduction current is now being played by displacement current, okay. To give you an idea of how this displacement current will be inside a capacitor, remember that d is given by q by a, and del d by del t will be, and what is the charge that is there? That would be C into V. For a capacitor, charge is C into V divided by A, right. So, del d by del t will be del by del t of this quantity, which I can obtain by removing this C and A outside here, and then say that del V by del t. Now, C by A, what is del V by del t? This was V0, omega V0 cos omega t, correct. So, there is C here, C can be expressed as epsilon A by d omega V0 cos omega t. There is a in the numerator, A in the denominator, that cancels out with respect to each other, okay, and then you get epsilon omega epsilon V0 by d cos omega t. This is the current density, right? This is the displacement current density. To actually get the total current, I need to multiply this one by, or I need to integrate this one by the appropriate. So if this is one of the appropriate vectors V0, then I need to integrate this one over the surface area, right? So when I do that, I see that this is simply, since this is perpendicular to the surface, this would correspond to simply multiplying this one by the total area A, right? So this expression, the total current which would be because of the displacement would be equal to omega epsilon A V0 by d cos omega t, and if you see what is that we have written earlier, this is exactly the same current, the charging current IC that we have obtained here. So see, the charging current is omega V0 epsilon A cos omega t divided by d. So this is precisely the same current that we have obtained. So you have a charging current IC which is then converted into displacement current inside the capacitor. Okay. So this is how the current continuity is ensured, and we again at the outside there is charging current only, right. So outside there is charging current, so that there is a continuity of the current ensured. Okay. Well, this analysis should have convinced you that the addition of this displacement current was a very important step. If this has not convinced you, let us look at one other simple example. Okay. I will not carry out the analysis for this one, but I will just give you the flavor of what is involved. Suppose I consider a charge, okay, let us consider a positive charge which is moving with a certain velocity. Okay. So let us say the charge is moving in this particular direction with some velocity v. Charge moving with a velocity obviously constitutes a current, right. If I consider a loop, okay, this loop again, it could be in this direction. I am not very rigorously considering the direction of the loop. For this loop, will there be a magnetic field? Well, there will be a magnetic field provided I take surface which would go through this point, right. So at this particular time, I have to consider a surface S1, okay, which would just connect to the charge, and this surface has to change as the charge moves along this particular direction. But the point is that at this instant of time when the charge is located at this point, there, if I consider a surface that is just touching or just imaginarily passing through the charge, there will be a current density because current is moving, V is there. So this is the direction for the current density, and this current density, the component of current density along normal to the surface will give me the current enclosed, and there would be essentially a magnetic field, correct. Now if I did not have displacement current, there is actually no conduction current. I mean, there is no wire which is actually carrying this charge Q along the direction for I enclosed. There is no wire here. So whatever that is there, that must have been only the electric flux density changing through this loop, or there is a displacement current, because I could very well imagine this surface S2 which would not enclose the charge or which would not pass through the charge, and hence would not give you any current, right, and would not give you any magnetic field. So this current enclosed when for the surface S1 is simply because of the displacement current, okay, and not because of the conduction current. And it is true. Why? Because a charge in motion which is changing its velocity would not introduce static electric field, it would actually introduce a time varying electric field, right. If the charge is moving with a certain velocity and its velocity is changing with, its velocity is moving, then there will be time varying electric fields introduced. The electric field will not be static anymore. So this addition of displacement current actually completes Maxwell's equations, and they form the basis for all of the classical electromagnetic theory, from transmission lines, waveguides, optics, antennas, microwave circuits, low frequency generators, AC generators, DC generators, machines, and any kind of electromagnetic application that you have in mind which utilizes charges, currents in motion and the corresponding fields which are interacting. There are only certain set of equations called Maxwell's equations which are sufficient to describe all these phenomena. Okay. So let's write down these equations once and for all to show you where we are at this point, and from now onwards we will consider some ramifications of these equations. Okay. So let me write down the equations in the integral form here, okay, and then write down the equations in the differential form. So we have Faraday's law. What is Faraday's law? The EMF induced, right, which is given by the integral of E over a certain loop must be equal to minus del by del t integral of B dot ds. Remember, Faraday's law actually has two types of relation, right, one where the path is varying and one where the field is varying, but both are essentially equivalent, right. In words, this would be EMF induced is equal to minus d psi m by dt, where psi m stands for magnetic flux. Okay. Next law is Ampere-Maxwell law. Okay. Ampere-Maxwell law states that the magnetomotive force, which is given by the line integral of H, is given by integral of J dot ds, which is the conduction current, plus the displacement current del d by del t dot ds. Okay. Again, I am not assuming that the paths are all moving with respect to time. In words, this is magnetomotive force is equal to conduction current density plus displacement current densities. Okay. And displacement current density is because of the change in electric flux density. Okay. We have two laws which are divergence based, and these are called as Gauss's law. Okay. One for electric fields and one for magnetic fields. So for the magnetic field, del dot B is equal to 0, and for electric field, del dot D is equal to charge distribution rho v, right. Of course, the conventional way of thinking about del dot B equal to 0 is that there cannot be any single magnetic charges. There are no magnetic charges found anywhere in universe. So if there was some magnetic charges that were found, you have to replace them with magnetic charge density, but this is highly unlikely to be found, and even if it is found, it has really no bearing on the electromagnetic phenomenon that we have already studied, okay, because these are not found everywhere. They are supposed to be very extreme, they are supposed to be extremely rare, if at all they are found. However, charges are found in abundance, and charge density is related to the divergence of, oh, I am sorry, I was supposed to be writing the integral form. So let me write down the integral form for this. Integral form is B dot ds is equal to 0, integral of d dot ds is equal to charge enclosed, right, and the corresponding differential forms are, and in both cases whatever I was saying was essentially the same. So for the differential form, Faraday's law becomes curl of the electric field equals minus del B by del T, and Ampere-Maxwell law becomes curl of H is equal to J plus del D by del T. Please note the sign over here, and two Gauss's laws become del dot B equal to 0 for magnetic fields and del dot D is equal to charge density for electric fields. These are the four Maxwell's equations. Now, in addition to these equations, you also need to consider three other equations. One equation is del dot J is equal to minus del rho V by del T. This is the continuity equation, current continuity equation, which states that in any given region there will be current only when the charge distribution there is actually changing, decreasing. Okay. Then we have Maxwell's equation written in terms of E, B, D and H, okay, but we have to relate them. How do we relate them? D will be epsilon 0 electric field plus P, where P is the polarization. When there is matter involved, P kind of relates the electric field to the matter, whatever that is happening in the matter, right. So this is the relation for D and E. This P for simple media will be proportional to electric field, and for complicated media it could be non-linearly dependent on electric field, it could be dependent on electric field applied some time ago, it could be dependent on electric field applied somewhere in a different direction. Okay. So all these complicated cases are possible, and they actually lead to very interesting properties of electrical properties of materials. There is a corresponding relation for B and H, which is even more exotic. This is mu 0 H plus mu 0 M, where M is the magnetization, and that describes how the materials have to be modeled: diamagnets, ferromagnets, ferrimagnets, antiferromagnets, all paramagnets. All these magnetic materials are characterized by different forms of magnetization M, compared to the electric relations or electric materials, magnetic materials are mostly nonlinear and exhibit hysteresis. Okay, so they are not that easy to work with compared to electric materials. Okay, and magnetic materials are also strongly anisotropic compared to most electric materials. These equations that relate DEP, BHM are called as constitutive relations. Constitutive relations are those which tell us how the electric field would behave inside a matter and how the magnetic field would behave inside a matter. Okay. So, the integral form of the equations or the differential form of the equations, whichever you use, these set of equations plus the addition of 3 equations, and in fact in the constitutive relations you are again going back to Maxwell's equations to analyze what is happening. So, in a sense that constitutive relationships have already been covered in Maxwell's equation. So, in addition to these 4 Maxwell's equations, the continuity equation is a conservation equation that is sufficient to describe all of classical electromagnetic theory. Okay. There is one additional form of these equations which are useful for us. Okay. And this additional form results when we assume the time variations of the electric fields in the form of a phasor. What do I mean by that? If the electric field, let us say, has certain value E0, right, it is pointing in a certain direction E0, but with respect to time it is changing as some sine or a cosine, or in general changing as e to the power j omega t, right. So, it is actually a sinusoidal wave which is pointing in a certain direction, but with respect to time it is changing as a sine or a cosine wave, okay, or in general a complex exponential way. Okay. We assume that all the fields are changing like this. So, D will also be pointing in a direction, but it would be varying with the same frequency. H and E would also be varying as H0 e power j omega t, and B would also be varying as B0 e power j omega t, right. In this case, what will happen to the differential form equations? Well, if you take the curl of this electric field, you will see that this would be curl of E0 e power j omega t must be equal to minus del B by del t, and B is B0, and time variation is happening only on e power j omega t. So, I can pull that I can differentiate e power j omega t to get j omega, and then I get B0 e power j omega t, right. So, you see here that this is E0 e power j omega t, nothing has happened because I have applied the curl to this one, that is presence of E j omega t hasn't really done anything to this, and this E0 j omega t is nothing but electric field itself, and B0 j omega t is nothing but magnetic field B itself, right. So, the curl equation actually becomes minus j omega B, with the understanding that electric field is pointing in a direction given by the vector E0, and it is varying with respect to time as a sinusoidal or a cosinusoidal function as of frequency omega, right. So, what really has happened is we have replaced this del by del t operator by multiplication by a factor of j omega. Okay. So, with this I can actually write down all the other forms. I will leave them as an exercise to you. I have curl of H is equal to j, there is no time variation there, but there is a del d by del t there. So, replace the del by del t by j omega, and this becomes d. Okay. Then we have del dot b equal to 0 and del dot d equal to rho v, no change in these two equations. The continuity equation becomes del dot j equals minus j omega rho v. Okay. So, these equations are known as harmonic form of equations, or sometimes to emphasize that this harmonic motion is happening in time, they are called as time harmonic electromagnetic fields. Okay. This is the time harmonic field expressions for electric and magnetic fields. So, we have seen these different equations. Let us actually see whether there is some arbitrariness included when we are writing the solutions, okay, for the Maxwell's equations. Let us consider an ideal dielectric, okay, and for this dielectric, if there is a charge sitting somewhere, then the D field for the static case will be q by 4 pi r square in the direction of R. Of course, this D field would also have been equal to epsilon times E, where epsilon is the permittivity of the dielectric that you are considering. So, you have a charge here which is Q, and I am looking for the D field around distance R at this point, and this D field is given by this expression. What if this charge is actually varying slowly with time in the form of, say, some sin omega t, right? If that happens, then one might reasonably expect that D would also start varying slowly. The key word here is that it is actually varying very slowly. Okay. In technically, this term is called as quasi static, okay, or sometimes this is called as synchronous variation. Okay. Assume that the frequency omega is very small. Okay. In that case, the charge quantity of the charge increases slightly, because when it is getting multiplied by q sin omega t, when it increases slightly, D field would also increase slightly, but in phase with whatever the charge variation. Okay. So, we are neglecting all the other propagation effects for now. So, D might be expected, you might expect that this would also be equal to q sin omega t divided by 4 pi r square. Okay. This would be equal to epsilon E. So, clearly E for the time varying case will be equal to r hat q by 4 pi epsilon r square sin omega t. Now, the question is whether such an electric field will be the solution of Maxwell's equation. We will try to find this out. Okay. The point to note here is that electric field is radially outward. Okay. It might be changing with respect to time, that is, the magnitude of the electric field might be changing with respect to time, but the direction of the electric field is all along radial direction. In fact, this r hat q by 4 pi r square can be considered as some E0, right, the direction in which the electric field is pointing, and this sin omega t is nothing but imaginary part of e power j omega t. So, this is precisely the form that we actually used earlier to write down the time harmonic solutions. Okay. In these earlier expressions, you could have used h0 cos omega t or h0 sin omega t as well to get the same relationships, okay, or similar relationships. Okay. So, here this is an example of electric field varying sinusoidally, okay, and pointing in a particular direction which is radial here. What is the curl of this electric field? We know that this sort of an electric field does not really have any curl, because you consider a small region over here, okay, over which you are trying to evaluate the curl, right. In this region, as many lines are going in, as many lines are coming out. There is really no curl for this electric field, right. So, because of that, you have this other equation which is curl of electric field, right, is equal to minus mu del h by del t, assuming that the material medium has a constant permeability mu. So, this seems to indicate that curl of electric field must be equal to minus mu del h by del t, but this must also be equal to 0, because E field has no curl. Electric field is pointing all the time along radial direction. Therefore, this equation would mean minus mu del h by del t must be equal to 0. The implication of this is that h must be either a constant vector, okay, or must be 0. Now, is this consistent with the other curl equation? Unfortunately, no. Remember, we are considering a perfect dielectric, therefore, the J term, the conduction current term will be equal to 0, and since we are considering an ideal dielectric, this displacement current can be written as epsilon del E by del T, correct, and because curl H is constant or 0, curl of H will also be equal to 0. This implies that this quantity must be equal to 0. Since epsilon is not 0, the solution is that E must be either constant or 0, neither of which is compatible with the assumed solution. So, the bottom line here is that quasi static solutions, okay, are not always solutions in general situations.